How's it going, everybody? Welcome back to DR Electronics. In today's video, we're going to be going over how to use DMA and Timer Channels in the STM32 Cube IDE. I needed both of these for a recent project involving an MQ2 gas sensor, which I actually covered in my previous video. If you haven't watched that, check the description below. And today we're going to be going over the purpose of DMA and Timer Channels, the IOC setup that I used, along with a code walkthrough explaining each function and variable that I defined. So let's jump into it. So before we use direct memory access, we need to understand why we need it in the first place. In the case of my project, I'm obtaining two sets of ADC values, one of the MQ2 gas sensor and another of a 3.7 lithium ion battery. Normally you would use the HAL ADC get value function and set that equal to your variable. However, this can only store one set of ADC values, not multiple, and my microcontroller only has one ADC channel. That's why I need DMA, as it can store multiple channels of data automatically in the memory without the intervention of a CPU. And we'll further discuss in the code how I set this up along with the timer channel. In regards to the timer channel for this project, this I figured out more through experimentation rather than knowing beforehand. So when I was typing up the code and generating it, I noticed how when my voltage was below 2.5 volts and I would have the LED blink on and off every 500 milliseconds, the UART terminal output would slow down. What I didn't realize was I was creating what is known as a blocking method of operation. This intentionally slows down the code so that the LED can properly blink. And I don't want this to happen, as I need the UART terminal to continuously output the ADC values of my gas sensor, the battery voltage, and the actual voltage of the battery itself. And the only way to do this, as far as I know, is a timer channel, as it can essentially set the amount of time that the LED is going to blink on and off internally in the code with a clock source, not through the HAL GPIO right pin set and reset function along with the HAL delay that you would normally use when blinking an LED. And if we can see here, I actually got this formula from an STM32 book that goes over extensively how to use the HAL IDE along with multiple projects. I will provide a link for this in the description. We can see here that I is the required interrupt time in seconds, and A is the value loaded into the auto reload register. And this is what we need to use in order to properly set up the Cube IDE so that the LED blinks at the intervals that we want. And once again, I will be going over this once we cover the IOC section. In terms of the hardware used for this demonstration, I'm using a Nucleo L476RG. And to the right, we could see here I have the pins highlighted in yellow. I have 5 volts for the MQ2 gas sensor, PC3 for the LED that we're going to be blinking on and off every second, PC0 for the gas sensor analog pin, and PC1 for the analog pin of the voltage that I'm reading across a resistor. I'm placing a resistor across this voltage in order to limit the amount of current flowing through that pin. You don't necessarily need it, although it doesn't hurt to have, and resistors are fairly cheap, so it's not like it's adding a lot to the circuitry. We'll now go over the IOC setup. In regards to our IOC setup, we'll first start off with the pin out and configuration. Looking at PA2 and PA3, we can see they're tied to USART2 TX followed by USART2 RX. If we go under categories, connectivity, USART2, we could see that we have an asynchronous mode of operation. Hardware flow control is disabled with a baud rate of 115,200 bits per second, a word length of 8 bits, no parity bit, and 1 stop bit. Our ADC channel is tied to PC0 and PC1. It's ADC1. And if we go under analog, ADC1, we can see that IN1 and IN2 are set to single-ended mode of operation. If we set them to differential, that would mean we would have 4 pins in total, which is just not necessary for what we're trying to accomplish. Under the parameter settings here, we could see that we have an ADC with a 12-bit resolution. Data alignment is set to the right. We have scan conversion mode enabled, followed by DMA continuous requests enabled, as we want to continuously get the ADC values from our USART terminal. Looking further down here, we could also see that we have the regular conversion mode enabled and the number of conversions set to 2, as we're getting 2 different ADC readings. We also have 2 ranks. Rank 1 is set to channel 1 because PC0 is set to IN 1, and rank 2 is set to channel 2 because PC1 is set to IN 2. And the sampling time is set to 640.5 cycles. This is the maximum amount of samples that I could get with the L476RG. If we look under our DMA settings, we can see that ADC1 is set to DMA channel 1, the direction is peripheral to memory, priority is low, and we set the mode of operation to circular. Regarding the GPIO output, in order to blink the LED on and off, that was merely by just clicking on the pin, scrolling down to GPIO output, and clicking that. That's all you need to do in order to actually set the pin so that it can blink the LED on and off. In regards to our timer channel, if we go under timers followed by timer 2, we could see here that slave mode is disabled, trigger source is disabled, and our clock source is set to internal clock. Channel 1 is disabled, and channel 2 is disabled, along with channel 3. The prescaler value that we set here is a 16-bit value. This is set to 39,999. Our counter mode is down, and our counter period is at 1,999. Now, keep in mind that in order to actually calculate the value loaded into the auto reload register, you need to know the required interrupt time that you want for your LED to blink on and off in seconds, and that's what we defined here. We also have the internal clock division set to division by 2, auto reload preload set to enable, and the master slave mode disabled along with trigger event selection set to reset. We'll now look at the clock configuration of this project, and if you can see here for the PLL source mux, we have it set to high speed internal along with the system clock mux for PLL CLK, and we have the HCLK set to 80 megahertz, which is the maximum that the Nucleo L476RG can handle. So that's pretty much it in terms of what we needed to set up in terms of our pin configuration along with settings. And these settings I mainly got just from watching different YouTube videos along with referencing the book that I talked about earlier in terms of actually properly setting up your project. We're now ready to step into the code. So for the code here, we'll first start off with the header files that I included for the project. The main header file is self-explanatory. std.lib is a standard library file. stdio is a standard header file. And a string header file is for string characters. Here we defined a macro for the LED that we're going to be blinking on and off as GPIO Pin 3. Here the handle type definition is defined for our ADC, DMA, Timer Channel, and UART. This is all pre-generated code once you set up your IOC properly. Here I've defined some global variables. This is going to be the ADC array that we're going to be storing of our two separate ADC values. We then have another global variable defined as ADC count. This is set equal to the size of the ADC values that we're defining along with the size of the array. Here we have another global variable tied to our ADC MQ2 average along with our ADC voltage average. Here we have some more global variables defined as our voltage. This will be the conversion of the ADC voltage that we're obtaining. We have a result ratio for the gas sensor along with a voltage result ratio. RO is the onboard resistor on our MQ2 gas sensor module. I set that equal to 10. And for the message that we're going to be passing through the UART terminal, I set it to a length of 50 characters. Here we have some more predefined code from the HAL. And looking further down, we could also see that we defined another global variable for our ADC conversion. This lets us know when the ADC conversion is complete. Here we have a function defining the UART send string terminal, and we have the HAL transmit the address of the UART followed by the pointer to the message. The string length is the message that we defined and the number of characters along with the HAL max delay. Here we have a void HAL ADC conversion complete callback function. This can actually be found in the drivers of your project. So if you go to drivers followed by STM32 L4 HAL driver, then to SRC, we could see here that we have an HAL ADC file in which it has all your functions that you would need in order to properly use DMA. So if we simply copy this and do a Control F, we can actually find the function that we're using, which is seen here. It's a weak function because it can be bypassed, but basically you just want to copy and paste this into your code and set your ADC conversion complete equal to 1. This will let the program know that your conversion is done and it no longer needs to obtain values. Here we have a static float for our read sensor. We don't want this function to change ever, so that's why I set it to a static, and we have that set equal to a 32-bit integer of sample count along with a delay here to pause in milliseconds. Here we have a variable defined as I, our MQ2 ADC value, and our ADC sum1. Again, we have two ADC values that we're obtaining, and I set the first ADC sum for the gas sensor. Here I've created a simple for loop to essentially set I equal to 0 and loop until it is greater than the sample count. So here we're using the HAL ADC start DMA function in which we address HAL ADC1 and then we point to the ADC values defined in our array followed by the ADC count. MQ2 ADC value is then set equal to the first parameter of that array, which in this case is 0. The second parameter of that array would be followed by 1, and if there was 3 stored in that array, it would be followed by 2. We then set ADC sum1 equal to the summation of MQ2 ADC value. We delay for a millisecond, and then we set the average equal to the sum of the ADC that we obtained in the for loop divided by the sample count. We then return 0 and repeat the process. Here the static float battery voltage is very similar to the read sensor function that we defined. However, the only difference is we're taking that ADC value and we're setting it equal to ADC voltage times 3.3 F divided by 4095.0 F. I put this here because we want to take the unsigned integer and change it to a float value, and we don't want to lose any of our decimal points when doing this conversion. So we need this entire thing to essentially be a float. We then set ADC sum2 equal to ADC voltage and do the same process again. Looking at our void HAL timer period elapsed callback function, once again this is from our HAL drivers. So if we go under the timer channel here, we'll first copy this function, followed by a quick Control F to find it. And here once again we could see the weak void. Once again, this just ties into our timer channel, which points to the timer channel that we're using, which in this case is timer channel 2. And this is a very simple function. If the voltage is less than 2.5, toggle the pin, which we set to GPIO and the BAT LED macro that we defined earlier. In our main here, there's really not too much code. We just have the initialization of the GPIO, the timer channel, the DMA, and the ADC channel along with USART that we're using. In the while loop, we have the result ratio equal to the read sensor that we're getting. So this is the function that we defined earlier in which we defined the sample count and the pause in milliseconds. So I made the sample count here 5 and the pause 10 milliseconds divided by our resistor value that is on board. Then we have the voltage result ratio simply equal to the battery voltage with the same sample count along with the same delay, as we don't need to divide this value by RO in order to obtain the proper voltage that we're expecting. And here we have a while ADC conversion complete set equal to 0. The program does nothing. So when the conversion complete function is not equal to 0, we want it to run through the code and obtain values. When it is, we don't want it to do anything. And finally, by this, we have a serial printf message, which shows our MQ2 ADC value, our ADC voltage, followed by our voltage. And here the /t just represents a space, /r and /n represent new line, and then we're setting this to our global variables that we defined earlier, along with our UART send string message, which was defined as one of our first functions here. So that's just basically an overview of the code. The rest of the code here is all pre-generated when you set up your ADC channels, your timer channel, and your GPIO output in the IOC. So you don't have to write this part. And if enough people ask for this, if I get 5 to 10 people asking for the code, I will create a GitHub for this channel and begin uploading my code. If there are better ways to improve this code and make it more efficient, feel free to let me know, as I am still very much a beginner in learning C, but I figured it would still be a good demonstration to show you how everything is set up and kind of my thought process along the way. Real quick, we'll also just run the code and see the output that we're getting to show you that this does actually work. All right, real quick, just to show you that this code works, we'll upload it here. As you can see, the build had 0 errors and 0 warnings. Now that the build is done, we'll search PuTTY, set the connection type to serial, COM line for me is set to COM3, and the speed is set to 115200, as we saw earlier. Looking at our UART terminal, we could see here that we're properly seeing the MQ2 ADC value, the ADC voltage, and the voltage conversion that we did in our bat voltage function. If I adjust my voltage here, we can see that it is at 1.6 volts and it's updating automatically, which is great. My LED here is blinking on and off every second. And if I adjust the voltage back to say 3.3, the LED is no longer blinking. We see that the ADC voltage is also set to its maximum value of 4095. And the MQ2 ADC value is still generating 1551, 1552. If I grab a lighter here and I bring it close to the gas sensor, we can see that the value increases, and once I stop using the lighter, the value decreases. Now again, for this type of gas sensor, you wouldn't really want to use a lighter. However, this is the only gas concentration that I have that I could use as a demonstration. So this is pretty much all you should see in regards to the project. One thing that I forgot to mention that I just realized now, for the timer channel and its function here, what you want to add in terms of the period elapsed callback, just make sure after the if statement you have an else statement that the HAL GPIO write pin is set to reset. I noticed that if the LED was blinking on and off every second, and when it was at the high state when it was on, if you adjust the potentiometer above 2.5 volts, or in this case your power supply, the LED will stay on and stay set because there's no callback to ensure that when it's not at this given condition, it won't be off. So I just wanted to mention that here. So what was the overall takeaway for this project? What did I learn from this? Well, I learned that C programming can go pretty in-depth. There's a lot of basic concepts that you need to understand in order to write code and have it work, but then you could go further than that and make the code function and look nice in terms of setting up variables, setting up functions, keeping your main as short as possible, and just making sure that variables are properly being used in terms of their output, their type, and their definition. During my studies, I focused more on the hardware aspect of engineering and not so much firmware, and I figured instead of just reading books and starting from the very beginning of C programming tutorials, you're better off just taking a project that you want to do and learning along the way. Active learning is always better than passive learning. And I hope that this video helped you understand how to use DMA and timer channels. Now, if there's anything in this video that you feel could have been improved, or there was something with the code that you just didn't necessarily agree with in terms of how I set it up, please feel free to let me know in the comments below. Again, this is still very much a learning process for me, and I just wanted to share what I understood when going through this and how I figured it out, because it's very confusing to a newcomer and there's a lot of challenges you need to overcome. But once you do, and once you get a good establishment of how to actually write code, it gets easier along the way. So that's just going to be it for this video. Thank you all for watching, and have a great day.